Welcome everybody to See You at Work 2020, and welcome to our first lecture. Since this is an online lecture, you can watch it at your own pace. You can pause to study some of the slides in more detail, or even repeat some parts. Try to make use of this advantage. In fact, at some point we will ask you to pause the video in order to check some external material. All such material will be linked in the video description. After having watched this video, you should join one of the corresponding Q&A sessions in order to ask any questions. Even if you don't have questions at this point in time, you should still join the Q&A to see what questions others might pose. If questions come up later, you can of course always write us an email or use the comment section. We will try to keep an eye on it. Finally, we will have little quizzes in the middle and at the end of this lecture. You might want to have pen and paper ready by then. Good to go? Okay, this is the agenda for our first lecture. We will start by introducing some fundamental terms about optimization. Then we will give a brief historical overview over the subject. Afterwards, we will sketch some of the most important theoretic concepts of optimization, like duality or complementary slackness, without going into too much detail.
So that you no longer have to deal with my accent, I'm now handing over to my friendly robot assistant. Alexa, hold the lecture for me.
Thanks, Timo. And welcome everybody. This summer school addresses mathematical optimization problems. An optimization problem, in a general sense, consists of a problem where we want to assign solution values to a set of variables, subject to a set of constraints. Those constraints must be fulfilled, and the variables have to take values within their domain. This is the feasibility part of the problem. Further, there is an objective function, which for each possible assignment of the variables, gives us the quality of the solution. This is the optimization part of the problem. We say that the solution to an optimization problem is optimal if it's both feasible, and has the best possible objective function value among all feasible solutions. Typically, while solving mathematical optimization problems, there is a primal bound, which is the objective value of the best solution that we've found so far. This solution is also referred to as the incumbent solution. There is also a dual bound that gives us a bound on the best solution value that is still possible. Hence, the dual bound tells us whatever solution we find, it won't be better than this bound. Between this dual bound and the primal bound, we can compute a gap, and once this gap reaches zero, we have a mathematical proof that the incumbent solution is indeed optimal. Also, if it has not reached zero yet, we have at least a quality measure of how good our current solution is. As an example, think of a shortest path problem. In this case, what's the shortest path from SUSE Institute Berlin, which is where this summer school should have taken place, to TU Berlin, the university hosting it? If I enter this into Google Maps, it will give me a feasible solution for that problem. There is a path which is 8.07 kilometers long. Is that an optimal solution? Well, first of all, Google Maps computes heuristic solutions, not exact shortest paths, and also, it's with respect to a different objective than what I've been asking for. Google Maps computes the fastest path and not the shortest path. So, most likely, it will not be optimal, but it is of course a feasible solution for a path from SUSE Institute to TU. It is even more easy to compute a dual bound. This is the B line, sometimes also referred to as the crow flies. This is 6.74 kilometers from Zib to TU Berlin. This means that the solution that I got out of Google Maps has a gap of about 16.5% with respect to this dual bound. We don't know yet what the shortest path is, but whatever it is, it will not be more than 16.5% worse than this 6.74 kilometer bound. Let us do a little challenge here. Try to think of two places that are at least 500 kilometers apart. That's about 310 miles. Go to the linked webpage, find out the length of the fastest path in the B line, and compute the Primal-Dual Gap between the two. Who can come up with two places that lead to a really small gap? Post your results in the comments below. This is a first example where different data can lead to very different algorithm behavior, here in terms of the solution quality, even though the underlying problem is the same. Shortest path is an example of a graph optimization problem. In the beginning of this summer school, we would like to concentrate on more general optimization problems, namely linear and integer programs. A linear program, or LP, is an optimization problem, where we optimize a linear objective function, with respect to a set of linear constraints, and all our variables are assumed to take real values. Typically, an LP is written in the standard form, which you can see on the slides. In standard form, all linear constraints are given as equations and the variables are required to be non-negative. The set of feasible solutions for this problem defines a polyhedron. A polyhedron is a convex set. The fact that we are optimizing a convex function over a convex set makes this a problem easy to solve. Here, easy means that it is solvable in polynomial time. Furthermore, we have the notion of basic solutions of an LP. We will talk about this later, as it is an essential component for many LP and IP solving algorithms. We mentioned the standard form, but there are very different ways to write down linear and integer programs. Essentially all of them are equivalent and can be converted into each other. First of all, you could use a maximization formulation instead of minimization. One can be converted into the other just by multiplying the objective function vector by -1. Then of course, you can directly convert an equation into two inequalities if you prefer an inequality representation. If you want all of your inequalities to be of the same type, less equal or greater equal, then you can multiply them by -1. Inequalities can also be casted into equations by introducing slack variables. A slack variable is a non-negative variable individual for each of the inequalities which captures the quantity which is missing to reach equality. In mathematical optimization, most of the times, we assume variables to be greater or equal 0. If you have unbounded variables, you can convert them to two bounded variables, one of it capturing the positive part and one the negative part. And if you prefer an unbounded formulation, then you can consider the bounds as a simple type of linear constraints and add them to the constraint matrix. Integer programs are often stated in an inequality formulation, and not as equations. As we just saw on the previous slide, this does not really matter. We can easily convert one formulation into the other, both are equivalent. An integer program, or IP, is an optimization problem where we minimize a linear objective function of a set of linear constraints, and we require all our variables to be integer. We get the so-called linear programming relaxation if we drop the integrality requirements and only keep the inequalities. In the picture here, you see the LP relaxation as a blue shaded area. The set of feasible solutions of the IP is shown as thick dots, the green one is the optimal. Recall that linear programming is easy because we optimize a convex function over a convex set. For an integer program, the set of feasible solutions is not convex, it is not even connected, it's a discrete set. In our example, it is 7 feasible points. This non-convexity is essentially what makes integer programming an NP hard problem. Finally, I would like to mention mixed integer programs. A lot of practical applications fall into this category. A mixed integer program, a MIP, is an optimization problem, where we minimize a linear objective function of a set of linear constraints. We require some of our variables to be integer, others might take real values. Thus, the set of variables is partitioned into a set of integer variables, and a set of continuous variables. Again, the solution set is discrete, sometimes also referred to as a mixed integer set. In the example in the picture, the mixed integer set consists of 4 different parts. Let us now get a brief overview of the history of linear programming. When did it all start? Solving linear equations, not necessarily with an objective function, is something that people have been doing for a very long time. Already the Egyptians and Babylonians considered the solution of linear equations. They did not describe concrete algorithms in their papyruses. They rather put down their knowledge in form of examples. Of course they didn't use the notation that we use today. But actually roughly at the same time in China, mathematicians already described what we would call Gaussian elimination. So the ancient Chinese indeed had an algorithm for solving linear equation systems. As a fun fact, Gauss himself, to which we typically attribute Gaussian elimination, did not formally describe it. He just used this in his books and said, well, obviously, this is how you would solve a linear equation system. Let's take a big leap in time. In 1827, Fourier described a variable elimination method, not for equations, but for linear inequalities, which is today often called Fourier-Motzkin Elimination. Motzkin rediscovered the same method, not being aware of Fourier's work, in 1936. This particular method is interesting, because Fourier-Motzkin elimination can be turned into an LP solver, by just adding one single variable and one additional inequality. Thus, we can cast solving an optimization problem into solving a feasibility problem. This is an important observation and useful for many theoretical considerations. Of course, this is not the application that Fourier had in mind. Linear programming in its modern form was formally described more than 100 years later. The typical credit for formulating the first linear programming problem goes to George Stigler, who formulated the diet problem. We see a simplified version of the diet problem here, with just two variables and two constraints. The original diet problem that Stigler formulated in 1939 consisted of 9 different nutrients, those are the constraints, and 77 different foods, those are the variables. What he wanted to achieve is to compute a cheapest possible diet, by fulfilling the nutrient requirements of an average man of that time, using only the given set of foods. Of course, Stigler didn't have a computer. That was before the time when the computer was invented. Still, he managed to compute a pretty good heuristic solution, which had an optimality gap of only 0.7%. From then on, linear programming rapidly developed. In 1939, Kantorovich laid the foundations of linear programming in a seminal article, which coined some of the terminology that we are still using today. Then in 1947, as the most important innovation for this field, Dantzig invented the primal simplex algorithm. This was the first algorithm to efficiently solve linear programming problems. Some 7 years later, Lemke introduced the dual simplex algorithm. It went a little bit unnoted at that time, because it seemed like a minor variant of the primal simplex. But actually, the dual simplex algorithm is by far the most important simplex variant that we use these days. Why is this? You will see later. In the following years, different teams of authors revised the simplex algorithms, making it more and more efficient. I would also like to point your attention to one of my favorite papers of that time, Computational Experience in Solving Linear Programs. A paper from 1953, and to the best of my knowledge, the first computational mathematical optimization paper ever written. This paper discusses 3 different methods for solving linear programs, and compares them computationally to each other. They actually implemented all these algorithms back in 1953, and tested them on the Standards Eastern computer. Isn't that curious? That was at a time where, for specifying the hardware that you're using, it was essentially enough to give a cardinal direction. We used the Eastern computer. In this paper, the authors discuss a lot of things that we will still consider today, like feasibility tolerances, discussions about memory limits, and so on. It was only shortly after that we had the first commercial LP code available, which at that time could solve problems with 71 variables and 26 constraints, in about 8 hours running time. In the 60s, LP really became commercially viable. It started to get used by oil companies, and then later different industries followed. In the 70s, the first commercial IP solvers were available, as you can see from this announcement. Mathematical optimization also can make you famous. In 1975, Kantorovich and Koopmans received a Nobel Prize for their work on the optimal use of scarce resources. Kantorovich, as mentioned before, laid the foundation for linear programming, and Koopmans made major contributions to an economic interpretation of linear programming. A lot of people think that George Dantzig should have been included into this list of laureates as well, but for whatever reason he wasn't.
Welcome back, everybody. I hope you enjoyed the video so far. Now it's time for our little quiz. I hope you have pen and paper ready. If not, you might want to pause the video now and get some. Okay, let's go. First question. Dantzig's simplex algorithm was published in A. 1947, B. 1954, or C. 1958. Second question. The set of feasible solutions for a MIP is also called A. a simplex set, B. a mixed integer set, or C. a linear set. And question number 3. Who formulated the diet problem? Was it A. George Stigler, B. Leonid Kantorovich, or C. Jean Fourier? Write down the answers, maybe take a little time to think about it. You might pause the video. And now, ready for the solution? Okay, here we go. Question number 1. Danzig's simplex algorithm was published in 1947. In 1954, the dual simplex method followed, and Gomery's cutting plane method was published in 1958. Question number 2. The set of feasible solutions for a MIP is also called a mixed integer set. The other two names I just invented. And the third question, who formulated the dyad problem? That was George Stigler. Leonid Kantorovich is known for his theoretical work on linear programming, and Jean Fourier we know from the Fourier-Motzkin elimination. Okay, so let's continue with the second part of today's lecture, and we will look a little bit into the theory of polyhedra and linear programming.
Polyhedra, first of all, are beautiful mathematical items to study. Already in ancient Greece, mathematicians studied the properties of polyhedra, the most prominent example being the 5 Platonic solids. Illustrations of polyhedra can be found in all periods of human history. Either as magic objects, as pieces of art, as a model of the universe, or just to showcase their symmetry. Till today, gemstones are almost always cut in a polyhedral shape. I would like to highlight the webpage polyhedra.tessera.li, where you can exploit a network of operations like truncating, dualizing, or expanding a polyhedron to get from any of the 120 regular convex polyhedral to any other. If you need a short break, I recommend that you pause the video for a few minutes, check out this web page and play with the interactive animations. Ready to continue? In this course, we are mainly interested in polyhedra because they have a close relationship to linear programming. Linear programming is about finding solutions to a set of inequalities in an n-dimensional real vector space. A polyhedron is defined as the intersection of finitely many half-spaces. Since each linear inequality defines a half-space, the set of feasible solutions of a linear program can be interpreted as a polyhedron. A polytope at the same time is defined as the convex hull of finitely many points. Furthermore, a convex polyhedral cone is the conic combination of finitely many points. A conic combination refers to a linear combination that uses only non-negative coefficients. You see that the concepts of a polyhedron, a polytope and a polyhedral cone seem closely related. The relation is given by this theorem about the representation of polyhedra. For any subset of the n-dimensional real vector space, the following are equivalent. First, P is a polyhedron. Second, P is the intersection of finitely many half-spaces. This is just the definition that we gave on the previous slides. You see the connection to linear programming. Third, P is the sum of a convex polytope and a polyhedral cone. The latter means that there exists a set of points V and a set of rays E such that the polyhedron is the convex hull of these points, plus the conical hull of these rays. You can see this in the picture. P is a polyhedron which is unbounded in one direction. You can represent P by 4 half-spaces that are intersected, or in LP terminology, by 4 linear constraints. Alternatively, you can represent P via these 3 extreme points, shown in red, and 1 extreme ray shown in blue. The representation via half-spaces, or inequalities, is also called the outer representation. The representation via points and rays is also called the inner representation of a polyhedron. There are some important special cases of n-dimensional polytopes. The first one is the simplex. A simplex is the convex hull of 0, and all unit vectors. This gives a polytope which has n+1 vertices. This means it can be described as the convex hull of n+1 points. It also has n+1 facets. This means it can be described as the intersection of n+1 inequalities. In 3-dimensional space, a simplex is also known as a tetrahedron. Secondly, there is the cross polytope, which is the convex hull of plus the identity vectors and minus the identity vectors. This means it can be described as the convex hull of 2 times n points. However, if you want to describe the cross polytope as an intersection of half-spaces, you will need 2 to the n many inequalities. Thus, there are polyhedra which require an exponential number of inequalities in the outer representation, but only a linear number of extreme points in the inner representation. There's also an example the other way around, which is the cube. The cube is the convex hull of all possible ±1 combinations in the n-dimensional space. This gives 2 to the n many extreme points. However, to describe a cube via inequalities, you only need 2 inequalities per dimension, one to bound it from below, and one to bound it from above. Thus, there are polyhedra which require an exponential number of extreme points in the inner representation, but only a linear number of inequalities in the outer representation. As you can imagine, having these 3 extreme examples is very handy for various proofs and counterexamples. Whenever you have a hypothesis about polyhedra, you should make a quick check whether it holds for these 3 examples. We already use the term vertices for zero-dimensional faces of a polyhedron. To learn some further notation, a one-dimensional face is called an edge. An n-1-dimensional face is typically called a facet. Note that each of the faces of a polytope or a polyhedron is again a polytope or a polyhedron. Try to think about why this is. Let's now go a little bit more into the theory. One very important theorem in mathematical optimization is the Farkas Lemma, which says the following. A polyhedron defined by an inequality system Ax less or equal than B is empty, if and only if there's a vector y, such that y is greater or equal 0, and if you multiply y with A, then you get the 0 vector. Furthermore, if you multiply y with the right-hand side B, you get a vector which is less than 0. So, what does this mean? What does the vector y tell us? Well, the first part means that you find a way to combine the inequalities in the system by only using positive multipliers. Well, of course, if you take an inequality and multiply it by a positive number, it still is a valid inequality. It defines the same feasible space. The same holds for adding 2 constraints, the sum of it will be feasible for all points that were feasible for the 2 original constraints. Thus, doing the vector matrix multiplication y times A just means that you sum up those valid inequalities, which is scaled by non-negative values, and if the polyhedron is empty, you can sum them up such that everything cancels out. So on the left-hand side you get y times A is equals 0, and on the right-hand side you get y times B strictly less than 0. Thus, the Farkas lemma tells us that for an infeasible linear program, we can derive a false statement by applying a valid combination of the inequalities. This only leaves the conclusion that the original system did not have a feasible solution. Since the Farkas lemma can also be formulated as either Ax less equal B has a solution or y A equals 0, y B less than 0 has a solution, it belongs to a class of theorems called theorems of alternatives. The Farkas lemma, in particular, is the foundation of all important higher-level LP theory, the duality theorems, complementary slackness, and so on. One way to prove the Farkas lemma is by using Fourier-Motzkin elimination. Fourier-Motzkin elimination is a method of successively projecting a polyhedron in n-dimensional space into a vector space of one dimension less, by eliminating one variable after the other. So, just sketching the idea here from a 3-dimensional space, you project down into a 2-dimensional space. From a 2-dimensional space, you project into a 1-dimensional space. In a 1-dimensional space it is actually very easy to compute a solution. You just have to check the validity of the bounds on the variables. You compute a solution in 1-dimensional space, lift it back up into 2 dimensions, and plug in the solution value for the one variable that you already know. You are again left with a 1-dimensional problem, you compute a solution, lift it up by 1 dimension, and so on. This is how you get the solution of your original system. In particular, this can be used to check whether the polyhedron is non-empty. So, if in 1-dimensional space you're left with a proper interval, then the original polyhedron was non-empty. Loosely speaking, this says that something that has a shadow must exist. As mentioned before, you can use Fourier-Motzkin elimination by adding an auxiliary variable z, with z equals the objective, and project this linear system onto z. The minimum value of z in the resulting interval will be the optimal solution of your LP. But is this also a practical approach? This is roughly how one single step of Fourier-Motzkin elimination works. You decide for one variable to eliminate, you scale all of the inequalities, such that this variable in all of them has a coefficient of +1, or -1, or 0, if it didn't appear in the first place. Then, you take a pairwise combination of all of these inequalities. Thereby you perform all possible eliminations of this variable, and derive a system, which has one variable less. Because you're doing this pairwise combination, in each step, in the worst case, you might square the number of rows. In a straightforward implementation, this leads to a running time of m to the 2 to the n. Obviously, a double exponential running time is absolutely not tractable in practice. With some tricks you can reduce this to a single exponential running time. While again, this is not really useful in practice for solving linear programs, Fourier-Motzkin elimination is essentially the best known method to transform polyhedra from the inner into the outer representation and the other way around. For this application, exponential runtime is already best possible, in a certain sense. Do you remember? We saw the examples of the cube and the cross polytope. One representation is of linear size, and the other one is of exponential size with respect to the underlying vector space. With Fourier-Motzkin elimination, we already made the connection between polyhedral theory and LP theory. Let us now look at duality. First of all, I would like to introduce the dual LP. So, let's assume we have this linear programming problem here, minimize C transposed x, the objective function, subject to ax greater or equal b, and x greater or equal 0. Assume we computed by whatever means a feasible solution. Say we just randomly guessed one and got lucky that it was feasible, and we want to know about its solution quality. Remember the concept of a primal-dual gap from the beginning of the lecture. So, how do we get a proof of solution quality? If we were very lucky, there would be one very simple case, if one of our constraints underestimates the objective function. Assume, for example, if our objective function is to minimize 2 times x1 plus x2, and we have one constraint which says x1 plus x2 must be greater or equal than 3. Then obviously, also our objective function always has to be greater or equal than 3, because the constraint is an underestimator for the objective. As a second observation, we can use a similar trick as in the Farkas Lemma. Constraints are invariant to scaling by a positive number. We can take any, or even all, of the constraints and scale them by a positive number. Further, the sum of two valid constraints is a valid constraint. Again, if each of them holds individually, then also the sum of them holds. As a consequence, this means that all conic combinations of constraints are, again, valid inequalities for the original inequality system. So, we could try to do the following. We could try to find a conic combination of all of the constraints, which is a maximal underestimator of our objective. We could try to find non-negative multipliers for the constraints such that they underestimate our objective terms and have a large as possible right-hand side. The task of finding such multipliers can again be formulated as a linear program, which is called the dual linear program. Okay. How do we get this? What's our task? We want to find a conic combination of all constraints that is a maximal underestimator for our objective. So, how could we formulate this? We want to do a conic combination of something. Thus, we need variable multipliers which should be greater or equal 0. This is what a conic combination means. We seek a combination of all constraints. So we use this vector y to multiply and add up our constraint system. The left-hand side, which will be a linear expression, should be an underestimator of the objective. So we want that this is less or equal than the objective vector c. Furthermore, we want this to be a maximal underestimator. So we want to choose our multipliers in such a way that they fulfill the feasibility requirement y transposed A less equal c, but at the same time, maximize y transposed b. That is, nothing else than a linear program. Maximize y transpose b, subject to y transpose A less or equal c, y greater or equal 0. This is the dual LP of the original linear program, and it gives us an estimate of solution quality. The scheme that we saw here is, that each constraint in the primal LP becomes a variable in the dual LP, and each variable in the primal LP becomes itself a constraint in the dual LP. The objective is inversed, so if you have a maximum in the primal, we have a minimum in the dual, and vice versa. Furthermore, the signs are inversed, greater equal constraints became less equal bounds. Less equal constraints become greater equal bounds. Consequently, equality constraints become free variables in the dual. If you follow this scheme, it's relatively easy to see that the dual of the dual, again, will be the primal. Let us now see what the dual LP really is. It is not only a neat relation. It is a proof. A proof of optimality. This is what the weak duality theorem says. So if you look at the maximal objective of the dual LP, the weak duality theorem says that this will always be less or equal than the minimum of the primal objective of A, which somewhat follows from the way that we constructed the dual LP. It is really trivial to prove the weak duality theorem just by plugging in the different definitions. Let us go through this from the start to the end. Y transposed B is less equal Y transposed AX. This follows from the constraint set of the primal. In the second step, where the equal sign is, we are just moving the parentheses around. Finally, we know from the constraints of the dual that Y transposed A is less equal C transposed X. Altogether, Y transposed B is less equal C transposed X. This is a one-line proof of the weak duality theorem. Just recently, Marco, who you will hear next week with a lecture on Dantzig-Wolff decomposition, named this his favorite tweet-length proof, and I can only support this. The strong duality theorem is harder to prove, and we won't do this here. The strong duality theorem is probably the most important and influential theorem in optimization. It says that two things. First of all, that the primal has a finite optimum if and only if the dual has a finite optimum. Secondly, this is very important, that these two optima are the same. So the minimum of C transposed X is the same as the maximum of Y transposed B, not only one is a bound on the other as in weak duality. The proof itself is not straightforward, but it only uses technology that we have been speaking about so far, weak duality and the Farkas Lemma. Altogether this says that we essentially have three possibilities. The standard case, let's say, is that we have finite and equal optima. The next common case is that one of the two is infeasible and the other one is unbounded. This is what you typically see for practically relevant infeasible problems. Technically, it's also possible that both of them are infeasible at the same time. Finally, I would like to speak about complementary slackness. So assume now, we've got a pair of a primal and a dual LP, and we have an optimal solution pair for these two. So, an optimal solution in the X variables for our primal, and an optimal solution in the Y variables for our dual. The theory of complementary slackness says the following. It either holds that a dual variable yi is 0, or the corresponding constraint in the primal is fulfilled with equality, or that both might hold at the same time. What this essentially says is that when you need a constraint for constructing the dual proof underestimator of the objective function, it has to be a constraint that's tied at the optimal solution. Look at the example on the slides. You can see the primal solution, the black point on the red objective function line. The dual solution will tell us that we can take the two constraints which are tied at this point and combine their normal vectors conically to the black objective vector, hence to an underestimator that's tied at this optimal solution point. We can get this underestimator by only using the two tight constraints. This is what complementary slackness tells us. The same holds the other way around. Either a variable in the primal is 0, or the corresponding dual constraint is fulfilled at equality. This is a good point to mention, that you can interpret the dual variables as something that's called shadow prices. If you have a non-zero dual value for a constraint, what does its value tell you? It's an underestimator of how much the objective would increase if you relax that particular constraint. Hence, in an economic interpretation, it is the gain that you could make by relaxing the constraint. There is another variant of the complementary slackness theorem that I would just like to mention for completeness, strong complementary slackness. There is a solution where the either slash or condition in the theorem is an if and only if. Essentially this says that you can build an optimality proof that involves all tight constraints. Since we already mentioned different possible primal and dual solution pairs, it is a good opportunity to mention primal and dual degeneracy. We mostly think about linear programming with the naive intuition that we have exactly one optimal solution, which is determined by exactly n constraints, that are tied at the solution, so there's only one possible primal and dual optimal solution. This situation is shown in the left picture. Actually, all the examples shown so far were of this simple form. However, this hardly ever holds in practice. At a second thought, what happens much more frequently is that you might still have only one optimal solution, but you have more than the n constraints, which are tight at the same point. This situation is shown in the middle picture. This is called primal degeneracy. But in reality, in most of the cases, the optimal solution is not unique, but you have an optimal polyhedron. So, not only do we have different possible dual solutions for one primal solution, but you also have different alternative primal solutions. This situation is shown in the right picture. This is called dual degeneracy. Try to think of an optimization problem with alternative optimal solutions. What about our shortest paths, for example, if we have square-shaped street blocks? Degeneracy, both primal and dual, can be exploited in some ways, in algorithms that we will learn in follow-up lectures. But most of the times, it is a burden.
Welcome back, everyone. This brings us to the end of our first lecture. And this means it is quiz time again. So let's get started. First question. If a dual variable has a non-zero value in an optimal primal dual solution, then A, the corresponding primal variable is non-zero as well, or B, the corresponding primal constraint is non-zero as well, or C, the corresponding primal constraint is tight. Question number 2. Describing a polyhedron as the set of all points in Rn with Ax less equal B for some matrix A and some vector B is called the standard form, or the outer representation, or the inner representation. And question number 3. The dual of minimized C transpose X subject to Ax greater equal B, X greater equal 0 is minimize Y transpose B subject to Ya equals C, Y less equal 0, or B, maximize Y transpose B, Ya equals C, Y greater equal 0, or question number C, maximize Y transpose B, Ya less equal C, Y greater equal 0. Take some time to think about it, maybe pause the video, and then we will show the solutions. 3, 2, 1, and here are the solutions. So, question number 1. If a dual variable has a non-zero value in an optimal primal dual solution, then the corresponding primal constraint is tight. So this is complementary slackness. Question number 2. Describing a polyhedron as the intersection of half spaces is called the outer representation. And question number C. The dual of minimized C transpose X, Ax greater equal B, X greater equal 0 is, well, we do have minimization, so the dual must be maximization. This only leaves 2 answers left. And then we see that the X variables are bounded, they are greater equal 0. This means the constraints in the dual must be inequalities. So this leaves the last answer, maximize Y transpose B, Ya less equal C, Y greater equal 0. Did you get everything right? If not, you might want to review the corresponding part of the presentation. Okay, this was it. I would like to say thank you and see you again for the next lecture. Bye-bye.